In the EDTA titration experiment, we are determining the concentration of calcium ions in a water sample by titrating it with a chemical called EDTA. That is part A of the experiment. In part B of the experiment, we would work with the total dissolved salts, working with conductivity. We are only doing part A. We are only determining the concentration of the calcium ions in a water sample by way of this titration with EDTA. Calcium ions are substances that are naturally in water. Calcium carbonate is the common version of that. Magnesium carbonate is also present in tap water. Depending on where what the source of the tap water is, there might be a lot of the calcium ions, magnesium ions present, or there might not be much. It depends on the source. We find that calcium ions, magnesium ions, other minerals make for hard water by when the water evaporates, that stuff is left behind as a solid, an ionic solid, that causes a buildup of the mineral deposits that we see in pipes, water heaters, etc. Basically, we don't like hard water. We don't like the presence of the calcium ions because also in our everyday life, they mean we need more soap. The soap combines with the calcium ions, rendering the soap not as useful, so we have to add more soap to get the same cleaning properties. So in our experiment, we get information allowing us to calculate the calcium ion concentration in a unit called ppm, parts per million. We will also convert that into concentration of calcium carbonate in the unit ppm because the standard is to work with calcium carbonate as opposed to just the calcium ion. The difference between the two takes into account the molar mass of calcium versus the molar mass of calcium carbonate. ppm is parts per million in units of mass, grams per million grams of solution. So it's grams, it's not moles that are in ppm. So that's why the concentration of calcium carbonate in soft water, let's say, is 60, versus if we had just the calcium ion concentration in that soft water, it would be 24, because the molar mass of calcium is less than that of calcium carbonate. Alrighty, so this unit ppm is the grams of the solute, so the calcium, divided by 1,000,000 grams of solution. Now, we will find that if we can convert, which we can, of course, using dimensional analysis, if we can convert from grams of solute to milligrams of solute for the numerator, and then 1,000,000 grams of solution to a liter of solution, then that unit of milligrams of solute per liter of solution is completely equivalent to ppm. How we make that conversion, so starting with our ppm on the left side, grams solute per million grams of solution, working with just the numerator, to go from grams to milligrams, we would be multiplying by 1,000 milligrams over grams. Now we've made the conversion from grams to milligrams. Looking at just the denominator, well, we have to assume that the water has a density very close to 1 gram per ml. So we would be just doing that one-to-one conversion. 1 gram is 1 ml. So now we're at the unit of ml, same number, 1,000,000. And then to go from milliliters to liters, we have to divide in the denominator by 1,000 to go from 1 liter, then to go from then milliliters into liters. So basically what we have done is to take our ppm equation on the left, multiply it by 1,000 and multiply it again by 1,000. So, and our units are milligrams per liter, and that's how that conversion works out, since 1,000 times 1,000 divided by 1,000,000 is 1. So we will find the handy unit for us for ppm in this work. In this experiment is milligrams per liter, milligrams of solute calcium per liter of solution. So EDTA, it's a big ion. It is a 4- anion, and it is shown on in this figure 1 on the left. Then the diagram just to the right of that leftmost one is showing it, but at the corners where the carbons are, it's just showing a corner. The C is left off. It's assumed to be there. The H's on the carbons are also left off so that we can see more easily the carbon framework in the molecule, the ion in this case. We know that the hydrogen are there. It has to be for the carbon to have its octet. So when that EDTA, it's a big complex ion there we see, when it combines with the calcium, it actually surrounds it by making 6 bonds from the EDTA to the calcium ion, and that is how it reacts with it. Here is our reaction between EDTA and the calcium ions. EDTA 4- plus Ca2 plus yield Ca EDTA overall 2- charge. And we see that the EDTA and the calcium ions are on a 1-to-1 mole ratio. Alrighty, so we will, through the titration, determine the amount of calcium ions present. Let's back up a moment. So we will start the titration with the water. We're using just Butte College tap water. We start with the water in the Erlenmeyer flask, and we have EDTA in the burette. We put some indicator into our Erlenmeyer flask that is a pink color when the calcium ions are not reacted with EDTA. So it's a pink color when the calcium ions are in solution as Ca2+. As we do the titration, as we add EDTA, well, it takes the calcium ions out of the solution by going through this reaction too, forming that calcium EDTA complex ion. The color slowly changes from pink to purple at the end point. When all the calcium has been combined with the EDTA, it's a blue color. At that point, we're at the end of our titration. That would be our end point. So, of course, we measured the initial volume of the EDTA. We measured the final volume of the EDTA in the burette. The difference of the two is the milliliters of EDTA used. We convert that to liters, multiply by the molarity of the EDTA solution, which I will give to you in the experiment video. And then we will have the moles of EDTA. Well, that will give us the moles of the calcium ions, since EDTA to calcium ions are on that 1-to-1 mole ratio. And then from that we will have the moles of the calcium ions. We will divide by the volume of the water in units of liters. I will give you the volume that we use in the experiment video. And we will have then the molarity of the calcium ions. What we will need to do from there is look back at equation 1 and go from units of molarity of moles of calcium per liter of solution to units of milligrams of calcium per liter. So what we have to do is go from moles of calcium ions to grams. That's using the molar mass. And then we go from grams to milligrams, just that 1,000-to-1 conversion, and we will have units of milligrams of calcium per liter of solution, that will be the ppms of the calcium ions. Now, what is recorded for hard water, soft water, etc., is not the ppms of calcium ions, but the ppms of calcium carbonate. So we then have to take into account the molar mass between the calcium and the calcium carbonate, and that's what's done in this sample problem here. So let's say we have 65 ppm calcium ions, and we want to convert that to calcium carbonate. So 65 ppm calcium ions means 65 milligrams calcium ions per liter of solution. We don't have to change the liter of solution part, we just have to change what's in the numerator. So we go from milligrams calcium ion to grams of calcium ions, so it's got the 1,000 to 1 conversion. Then we have to go to moles of calcium ions, so we use the molar mass, 40.08 grams per mole. Then we use the mole ratio between calcium ions and calcium carbonate, which is 1 to 1. Now we're at moles of calcium carbonate. Then we go to grams of calcium carbonate using the molar mass of calcium carbonate, which is 100.09 grams per mole. Then we finally go to milligrams of calcium carbonate using the 1,000 to 1 conversion. Ultimately, what that comes out to is taking the milligrams calcium ions and multiplying by 100.09 over 40.08, and that will come out to give us the milligrams of calcium carbonate per liter then. And so 65 ppm calcium ions corresponds to 160 ppm of calcium carbonate. What we would do is take that number and look at this classification table, and we would see that 160, that would be classified as hard water. Okay, we are not doing the second part of the analysis, this total dissolved salts part. The experiment overview, read that over, read through the experiment procedure so that when you watch the experiment video, you know what's going on. And you can, as usual, skip the pre-lab and go to the report where you will fill in data from the video. And your assigned water sample, okay, that will be Butte College tap water. I will give you the information you need to fill in this table, like the concentration of EDTA, the volume of the water sample we use, the initial burette and final burette reading, and that will then allow you to calculate the volume of EDTA added. We will only do trial 1, no trial 2, no trial 3, so the volume of the EDTA added will just be ultimately your average volume of EDTA. We're skipping part B, so ignore that part. And then for the calculations and results, so part A, EDTA titration, you will be able to calculate, as we talked about earlier, from the volume and the molarity of the EDTA, you'll be able to calculate the moles of it. You'll get the moles of calcium ions. They're on the 1-to-1 mole ratio between calcium ions and EDTA. Then you will determine the concentration of the calcium ions by taking into account the volume of the water converted to liters. Then you make that calculation from moles per liter to milligrams per liter, which corresponds to ppm. That's the one we talked about earlier, where you have to go from moles to grams and then finally grams to milligrams. And of course, going from moles to grams is using the molar mass of calcium. Then to get to the ppms of the calcium carbonate, you will take into account the molar mass of the calcium ions, the molar mass of the calcium carbonate, following that sample calculation. Now, for the class average, I'm going to, in the experiment video, give you water sources and the class average values for the calcium carbonate in ppms from those water sources. We are skipping part B, so ignore that. The questions. So you will be able to do question 1 based on your data. You're deciding of those water sources, are they hard or not? You can ignore the last row in that table. You are just going to write the water sources down and the hardness classification based on that table on the first page of this experiment. You can ignore the ground or surface source. Okay, number 2 you can ignore. Number 3, that is having you work with a reaction and you are writing out the net ionic equation for the reaction. You're making the calculation in part B and a calculation in part C, much as you have done in your calculation and results sections with the calcium ions. Okay, so that is the end of the report. So when you're happy with your report, scan it as a PDF file and submit it.